Alright guys, right now what I want to do is explain the whole arrow on the moon and how the trajectory of 0 impacts the fall time but doesn't affect the acceleration. So anyways, yesterday I gave you a project of a car that was driving and another force hit it. Let's do a new scenario. Let's pretend you're running towards a finish line. So there you are. Maybe not. There you are, running away in all your glory towards the finish line. Okay, as you're pushing and pushing and pushing, you are pushing this way with an acceleration of, let's just say, 2 feet per second, per second, per second. I think I said too many seconds. Anyways, as you're doing that, okay, you need to get to this point right here. But a strong gust of wind comes and blows you sideways. So naturally, your way that you're going to go is going to go like that if you keep just pushing forwards. What you end up needing to do, though, is readjust and readjust and readjust if you do go towards the X. However, if you just kept running with the 2 feet per second acceleration, you would accelerate right down this line right here. Okay, so your direction would change. You would have a new velocity. On top of that, your speed would change. Does the amount that you're pushing with change? No, you're still accelerating 2 feet per second. So acceleration due to gravity of a falling object that has been, say, trajected is still going to be 30 feet per second downwards as you determined it to be. So in actuality, it's 9.8 meters per second squared on Earth. It's always going to be accelerating at that. That's not going to be necessarily impacted. So that's what's happening in the scenario. You just keep pushing with 2 feet per second, but you're not going to end up in the same spot. And that's important because I gave you another scenario. What I gave you was this picture right here. And so let me just move that over there. Let me explain it again. Here you are. And we're going to take a little trip. We're going to go to the moon. Now you're red because your blood would boil in outer space. Anyways, yay. We're going to have a nice sweet little bow and arrow here. And we're going to shoot an arrow. Okay? From the bow and arrow. Here's the surface of the moon. When you're looking at it, it looks like it's flat. However, if we really made the moon much smaller, the surface you would actually see is like curved to. And something unique, there's a Verrazano Bridge in New York City. The architects, they made the span between the two towers so big that when they laid the foundations, they needed to take into account the curvature of Earth's surface. So keep that in mind, you flat earthers. Anyways, if we really zoom in, we start to see something like this. Okay, you got a circle right here, and this distance right here is only 5 feet. If we launch an arrow completely sideways, what you're actually doing is getting further and further away. So if you look, let me zoom in. This is a right angle when you launch it. However, now, if you're going back towards the way gravity is working, is it's acting towards the center of mass, so towards the center of mass of the moon, right here. Okay, if I'm making that angle back, my angle is changing. It's no longer 90 degrees right here. Okay, that's not 90 degrees. On top of that, well, this line right here and this line are the same distance. I made sure when I made this diagram to not change the length of that line so you could see that, wow, now there's all this extra room it has to fall. So obviously it's going to take longer to fall. That's what I was hoping you would see. The other thing some of you started to pick up on, though, is that, well, if you launch it completely sideways, you're getting further and further away from Earth's surface. That's what we're showing here. As this happens, it's still accelerating downwards. Let's just say on the moon, it's accelerating downwards at only 10 feet per second per second. And this is where things get crazy. Say I hit a golf ball. Now we're changing characters. I feel like golfing. We got this little guy, awesome golfer. He's swinging a golf club, and he's gonna hit a golf ball with his golf club, and that golf ball is gonna take off. Let's just say he hits a low liner right on the surface of the moon. Because there's no air molecules or particles, there's nothing to slow that down other than gravity pulling it back down to the Earth's surface. If you hit a golf ball at the surface hard enough, and obviously, I mean, it would need to be a few feet off of the surface, but let's just say you hit it hard enough, what could happen is that sideways velocity, even though it's moving sideways, as the curvature of the moon is changing, it's getting far and far enough away. It's getting far enough away from the surface at a speed equivalent to 10 feet per second per second. Well, gravity is going to be constantly going back the same way, so it's going to start to do this. Here's our moon. We launch it this way initially. It's going so fast that every time it's getting pulled down, it starts to turn. It gets pulled down, it starts to turn. It gets pulled down, it starts to turn. What we just did with our trajectory of 0 is did it perfectly so that it's accelerating inwards due to gravity with 10 feet per second. But then that outward force, which is definitely greater than 10 feet per second, that acceleration, well, it's going so perfectly that every time it's impacted, the resulting net force balances with that inward pull. What you're doing is creating orbit. So technically, you could create a situation on the moon. Make it green because everybody knows the moon is green. It's a joke, people. It's a joke. Anyways, so we have our golf ball. You'd hit it at the surface of the moon, and because there's no atmosphere, it would just keep orbiting and orbiting and orbiting. And this one is not in perfect balance. And what I'm showing you is something that would escape orbit because something else is happening too. Anyways, orbit would happen when those are perfectly balanced, and it would stay, and it would keep going around the moon like this, and like this, and like this, and like this, yay. Anyways, that would be perfectly balanced orbit, and it would happen on the moon because there's no atmosphere to slow down those particles. So if you hit it with enough force, and those two manage to magically balance out, that's how orbit happens. That's trajectory, and outward forces needed to balance. Now what I just showed was an escape velocity. If you notice this one, I got further and further and further away. The reason is this. I had posed a question to you guys. Posed two questions. I said, one, you're on the moon. And you're an astronaut, let's just say. The other one, you're on Earth. And these are obviously not to scale. The Earth in comparison is much bigger. Here you are on Earth, and I'm going to draw you a certain way because you're a little bit flatter. And here you are on the moon. And you're going to be a little bit taller because guess what? Your spine is not being compressed as much. You weigh more on Earth than you do on the moon. Because the force of gravity on Earth is much greater than the force of gravity on the moon. So, all that weight is a measurement of gravity's impact on mass. So you guys are going to have the same mass, the amount of matter, no matter where you go. But gravity has a stronger pull on that. In your videos, I wanted you to drop heavy objects and light objects. So we got like a 100-pound weight and a 10-pound weight. This one on Earth has a much bigger force downwards. This one has a much smaller force downwards. So gravity is going to impact them differently. It has a greater attraction with the 100-pound mass than it does with the 10-pound mass. However, both accelerate at the same speed. And, well, the reason is if you ever tried pushing a 100-pound weight, well, it takes a little bit more effort to get moving. Whereas if you push a 10-pound weight, it's going to take a lot less effort to get moving. So, this one, the 100-pound weight, takes a lot more force to get going. But luckily, the way gravity works is that the more mass something has, the more of an attraction it has to the other object. So, Earth being much more massive, like 100 pounds, and this like a 10-pound, this one has a much greater attraction. Anyways, that's why you weigh more on Earth. But things get weirder. So, when it comes to another question I had asked you, I said, when it comes to another question I had asked you, I asked, well, how come we're not, when we stand on the moon's surface, how come we're not, being pulled back to the Earth? And guess what? We slightly are, but at the same time, we're also slightly always being pulled to the moon. So if you were directly underneath the moon, sure, it has the smallest bit of pull on you. And what I wanted you guys to see, though, is that, well, distance you are from an object, the distance you are from an object makes things, have less and less attraction. That's why we can put things into orbit like little satellites. I don't know how to draw a satellite, so this is going to look awful. Anyways, that's my terrible looking satellite. And this satellite orbits around the Earth. And the reason it does is because it's out at such a distance. As the distance increases, gravity decreases. And I'm sure you guys know that. Like Tesla and all these other people are like, oh yeah, go to space and experience zero gravity. You're not really ever experiencing zero gravity if you go to space. That's not how it's actually working. You're still experiencing the gravity of Earth, just on a lot lower level. And you're moving along with a certain trajectory that makes you feel like you're not moving. So, anyways, the further you get away, the less gravity impacts you. So if that's the case, if you're standing on Mount Everest, on the top of Mount Everest right here, not even on it, gravity is actually less than when you were standing on the surface. So if you stepped on a scale on the top of Mount Everest, and I'm sorry for my terrible drawings, you would actually weigh less than you do if you stand on a scale at, say, the Earth's surface, or even better yet, go to Death Valley and you're a few hundred feet below sea level and you'd weigh more. Alright, so I want to show you back to this. So we just said that as you are on the moon's surface or any object surface, and the further you get away, the less gravity impacts you. Hey, Booga. You want to say hi?
Hi.
Yeah, okay. 5:40 in the morning. All right, so in this diagram then, if you notice, we're talking about this diagram now, we're getting further and further and further from the Earth's surface, the harder that everything is hit. Obviously, as we get further and further, gravity gets less and less. Hi, Booga. Which is going to be another factor or variable that we need to take into account. Anyways, I'm going to get going because this video is getting too long and Logan's here. I hope that this helped, and this will be something to pay attention to today and take some notes on.